Hey, in this tutorial we're looking at section 13.4, which is on special parametric curves. Okay, to sketch graphs of curves defined by parametric equations, we find turning points and axis intercepts. Or we can just use our calculator, which is always going to be the option that we'll go for when we can. Okay, so finding areas using parametric forms. Okay, using the parametric equation for a curve, the area under the curve is given by area equals from integral from a to b of y dx. Okay, summing in y equals y of t, okay, and d dt of x of t, we get our area from t equals t0 to t equals t1, y of t d dt of x of t dt. Okay, so it seems a little bit confusing there, but once we get into some worked examples, you'll see how that works. Okay. The length of the curve between t0 and t1 is given by our integral from t0 to t1 of the modulus of our v of t dt. Okay, so that's all the theory we've actually got. Okay, and we've got a couple of worked examples to look at. Okay, now if you've been following any of my other videos on YouTube, you'll know that most of the time we can get through a worked example in a page, but for the next couple we actually need to have a couple of pages free basically. So we'll see how we get on with our space. Okay, so we've got worked example 8. Okay, we're given a position vector r of t equals 2 cos of ti plus sine of 2tj. We know that t is an element of 0 to 2 pi. Okay, the first thing we want to do is find the gradient of the curve in terms of t. Okay, so what we need to do is find our derivative of our x of t and y of t. Okay, so we can say our dx dt, derivative of this is going to be negative 2 sine of t. Okay, and our dy dt, our derivative of this part here is going to be 2 cos of 2t. Okay, so what we need to do now is find dy dx. Right, and we know from our previous section that that's equal to our dy dt divided by our dx dt. And that's simply because using our chain rule we'd have to invert this one here. Okay, so what we can say then is we get our 2 cos of 2t divided by negative 2 sine of t. Okay, our 2's can cancel out and leave us with negative cos of 2t over our sine of t. Okay, so that's our gradient of the curve in terms of t. Okay, so what we need to do now in part B is find the values of t when the tangent to the curve is parallel to the x-axis, and hence find the turning points on the curve. Okay, so what we need to do is look at our derivative. Okay, and we need to set that equal to 0. Okay, and we know that cos of 2t can equal 0. Okay, but our sine of t can't equal 0 because it will be undefined then. So what we can look at here is when is cos equal to 0 in our domain, and we get our solutions 2t equals pi on 2, 3 pi on 2, 5 pi on 2, and 7 pi on 2. Remember when we've got cos of 2t, we expand out our domain. So we to 0 to 4 pi, find all our solutions. And then we divide them all by 2, so we get back to our domain that we want, which is t equals pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. Okay, so they're the t values. Okay, so what we need to do is actually find r of pi on 4, r of 3 pi on 4, r of 5 pi on 4, and r of 7 pi on 4. Okay, to finish this one off. Okay, so I think we'd all be pretty comfortable to sub in these values in for here. So I'll just simply write our answers. So r of pi on 4. What we should get for that is root 2i plus j. R of 3 pi on 4 is equal to negative root 2i minus j, r of 5 pi on 4 is equal to negative root 2i plus j, and r of 7 pi on 4 is equal to root 2i minus j. So, and we think of these as coordinates as well. So we can think of it as root 2, 1, negative root 2, negative 1, negative root 2, 1, and root 2, negative 1. Okay, so we're going to get our maximum turning points. Okay, are going to occur at so our max is going to be at our root 2, 1, or our negative root 2, 1, because obviously 1 is bigger than negative 1 for our y coordinates. And so our minimums are going to be at our negative root 2, negative 1, or root 2 and negative 1. Are going to be our minimums. Part C, we're asked to sketch a graph of the curve defined by the parametric equations. X equals our 2 cos of t and y equals sine of 2t. So this is a pretty cool looking graph actually. So you'll see it there in your textbook. What we find is we get our negative 2 to 2, and we get a graph that looks something like this. And as you can see in the book, that's what our calculator looks like. So for part D, we need to find the speed of the particle when t equals pi on 4 and t equals pi on 2. For part D. So we know that we know what our r of t is, and our r dot of t, well, we've worked out everything we need, so it's equal to 2 cos of ti, and 2 cos, our r dot of t is our negative 2 sine of ti plus our 2 cos of 2t, j. And so we need our magnitude of that. So it's going to be the square root of each of these parts squared, which is going to be our minus 2 sine of t squared plus 2 cos of 2t squared. We see here that we're going to be squaring our 4's here, so what we can say is we can get, so you're going to square our 2's and get 4's, so we can get 4 outside of our sine squared of t plus cos squared of 2t. Unfortunately we can't do a lot there. What we need to do now is let t equal our pi on 4. When we do that, we find that our magnitude of our r dot of pi on 4, we sub that in, pretty easy process, and we get root 2. When we let our t equal our pi on 2, again pretty easy process to sub that in to our equation here. Then we get that our modulus of our r dot of pi on 2 is equal to 2 root 2. So that's what we've got so far. For part E, we're looking at the area bounded by the curve and the x-axis can be expressed as, now it's our integral equation that we saw just a moment ago, which is our integral t equals t0 to t equals t1 y of t d dt of our x of t dt. Okay. We need to obtain a definite integral in terms of t for the area and showing using calculus that the total area bounded by the curve in the x-axis is 16 on 3 units. Okay, so part E, right, we're saying when t equals 0, okay, then we can say our r of 0, okay, our position vector up here, is our 2 cos of 0 I plus sine of 0 j. So r of 0 is going to equal just simply 2I. Okay, so we know our coordinates then are 2, 0. Okay, when t equals pi on 2. Okay, well, what we get is our r of pi on 2, okay, equals our 2 cos of our pi on 2 I plus our sine of our 2 times pi on 2 j. So our r of pi on 2, okay, is equal to actually 0. Okay, so we get the coordinates then of the point. It's actually our pi on, our 0, 0, our coordinates as well. Okay, so what we do then, okay, is really what this equation can become is our integral, okay, from t equals t0 to t equals t1. We'd say it's y of t, okay, and this part is really our x dot of t, okay, dt. Okay, so we know our y of t, okay, is our sine of 2t, okay, and we know our dx dt, okay, is equal to our negative 2 sine of 2t. Okay, so what we can say here then, okay, is when we think about our area from our 0 to pi on 2, okay, that's really only a quarter of our area all up. Okay, so what that's going to give us is just a quarter of our shape here. Okay, and that's because really we're looking at going from 0 to 2 pi. Okay, so what we're going to do then is say our area is equal to 4 times our integral from our pi on 2 to our 0 of our sine of 2t, okay, minus our, times our negative 2 sine of t dt. Okay, so what we get then is we can really say that this is equal to a equals our negative 16, okay, times our integral from pi on 2 to 0, okay, of sine squared of t, okay, cos of t dt, okay, and that's using our double angle formula on our sine of 2t, okay, is what we're doing, and then bringing out that that value there, our negative 4. Okay, so that means that we get an area, okay, of our negative 16 on 3, okay, times by our sine cubed of t, okay, will be our integral here from pi on 2 to 0. Okay, what we find there, okay, is in here we get our answer of negative 1, okay, which gives our area of 16 on 3 as required. Okay, so what we've got next, okay, in part F, did I leave myself 2 pages? I did leave myself 2 pages, so we might be running out of a bit of room here. So I thought I had left myself 2 pages for this one. Okay, for F, okay, the total length of the curve between the values t0 and t1 is given by our integral, okay, of t0 to t1 of our magnitude of our v of t dt. Okay, we need to set up a definite integral that gives the total length of the curve. Using technology, find the total length of the curve. Okay, so for this one, okay, our modulus of v of t, okay, is our modulus of our r dot of t, Okay, and we know our modulus of r dot of t. Okay, we were doing it earlier. Okay, here. Okay, what we can do though is we bring this 4 out, okay, as a 2. Okay, and again, okay, our total length. Okay, we're going to need to be looking at our 4 times it, just like we need to go 4 times our area. Well, our length of our curve is going to be 4 times the integral, okay, of pi on 2 to 0, okay, of our equation here, okay, which is 2 times square root of our sine squared t plus cos squared of 2t. Okay, well, of course, we can bring out our 2 as a common factor. Okay, integrating that is not nice at all, and that's where we can use our equation and we get the length of our curve S to be 12.1944 units. Okay, so I know I kind of squished that in up there, but it is calculator work, so hopefully we'll be okay. But the idea is, so modulus of V of t, well, we actually knew what our modulus of V of t was already, because we'd found that, okay, and we're integrating 4 times that, okay, because that part was from our pi on 2 to 0, was going to be only a quarter of the length of our curve. Okay, but thankfully it's symmetric, and that's why we could just multiply by 4. Okay, our G is show that the particle moves along the curve defined by the implicit equation, okay, y squared equals x squared on 4 outside of 4 minus x squared. Okay, that's what we're trying to show. Okay, so for part G, okay, we've got our implicit equation. So what we're going to use is we're actually going to use this equation and go, well, what is y squared? Well, we know y is equal to sine of 2t. So we can say, well, y squared equals sine squared of 2t. Okay, which we can expand out. Okay, and we can actually get that's equal to 2 sine of t cos of t squared, okay, using one of our identities, okay, which gives us our 4 sine squared t cos squared t, okay, to start off with. Now if we have a look at our right hand side, so that was our left hand side, okay, if we look at our right hand side now, okay, well, we can see that our x squared, well, our x is 2 cos of t. Okay, so we can say that this side is going to be our 2 cos of t squared on 4 outside of 4 minus our 2 cos of t squared. Okay, and we can simplify that down to being 4 cos squared of t sine squared of t. Okay, and so our left hand side equals our right hand side, okay, as required. Okay, so a little bit of work there that I just skipped through. Okay, but essentially we're going to be squaring our 2 gives us our 4, going to cancel that with our 4 down here. Okay, and then when we multiply through, this is also going to be our 4 cos squared of t, and when we multiply through we can end up getting our answer here, okay, with a little bit of work. Okay, because what we can do here, so the other thing that we can think about here, okay, is when I square that, I'm going to get 4 cos squared of t, okay, and it's 4 minus that, so we're bringing our 4 out as a common factor, and so it's 4 outside of 1 minus cos squared of t, okay, which is equal to sine squared of t. That's how come we get our sine squared here. Our 4, taking out as a common factor, is the 4 here, and our cos squared is what we get left with up there. Okay, so I think we're going to be struggling to fit in part H here, so what I'd suggest is that you actually just have a look through that, because part H is hence verify that the total area bounded by the curve and the x-axis is given by 16 on 3 square units. Now we had that before. Okay, the difference with H, okay, is that we're using our equation that we're given here, and we're actually going to integrate that. So you're going to rearrange, okay, get it for y, okay, and we're going to integrate our area there. Okay, difference is we're going to be going from -2 to 2. Okay, because we know there are values there. Okay, and we'll need to, if you follow through, we've got some of our non-linear substitutions that we need to do. Okay, change around our terminals and such, and we run through and get the same answers we got before. Okay, we do in fact have one more worked example, which again is going to be quite in depth. Okay, but as I said, I've given myself a bit more room here. We've got 2 pages, so we should be able to get through it. So, for worked example 9, okay, we're told that we've got a position vector given by RT equals 4 cos of t plus 4 cos of 4t, sorry, just cos of 4t, I, and 4 sine of t minus sine of 4t, j. Okay, we know t is between 0 and 2 pi. Okay, so for part A, we're going to be finding the gradient of the curve. Okay, so our gradient of our curve, again, we're going to have to find our derivatives of our x of t and our y of t, and then use our chain rule to find our dy dx. Okay, so we know our x of t, okay, well that's equal to our 4 cos of t, okay, plus cos of 4t. Okay, so our x dot of t, okay, when we take the derivative of that, it's going to be our minus 4 sine of t, okay, minus 4 sine of 4t. Similarly, our y of t is equal to our 4 sine of t minus sine of 4t. So our y dot of t, okay, is going to equal 4 cos of t, okay, minus 4 cos of 4t. Okay, so what we need to do, okay, is find our dy dx, and through our chain rule we know that's y dot on x dot. Okay, so that means we're going to get our 4 cos of t minus 4 cos of our 4t over our minus 4 sine of t minus 4 sine of 4t. Okay, which can of course simplify down to be cos of t minus cos of 4t over sine of t, okay, plus sine of 4t. Okay, so a little bit of work there. Now, sorry, I've just realised I put that around the wrong way. Okay, because we're bringing negative 4 out, so these are going to switch. Okay, so that's actually going to be cos of 4t minus cos of t. So sorry, I just put that around the wrong way. Okay, so we'll look at part B now. Okay, part B is find the speed at time t. Okay, well, our speed is given by the magnitude of r dot of t. Okay, well, our r dot of t is equal to this I plus this j. Okay, so it's going to be the square root, okay, of our minus 4 sine t minus 4 sine of our 4t squared, okay, plus our 4 cos of t minus our 4 cos of 4t squared. Okay, so to save a little bit of room there, okay, really what we're going to do is you'd expand them out just like you would quadratic brackets, okay, and what we end up getting, okay, is we get the square root, okay, of 32 outside of 1 minus cos of 5t, okay, which is equal to 32 times 2 cos squared of 5t on 2, okay, using some of the identities, okay, which means we get a value of 8 cos of 5t on 2. So whilst this looks quite nasty up here, it does actually simplify down to something quite nice. Again, if you want to see some of this, the simplification there, it does go through it in the textbook. Just as I said, quite a long worked example, so we want to get through it. Okay. For part C, we need to find r dot of t, r of t. Okay, so what that means, okay, is we need to multiply our x dot. Okay, so this is going to equal our x dot of t times our x of t. Okay, plus our y dot of t times y of t. Okay, so that's going to equal our x dot of t. Okay, was our minus 4 sine of t minus our 4 sine of 4t. Okay, times by our 4 cos of t plus cos 4t. Okay, plus, I'm just going to move down our page here, y dot, which is our 4 cos of t minus 4 cos of 4t, times by our 4 sine of t minus sine of 4t. Okay, so you can see there's a little bit there. Okay, again, you can see there's a, what we do is we can expand out our brackets, okay, and essentially collect like terms, and you see there's quite a lot of terms by the time we multiply out these brackets, because we're going to be a term, we've got that term by that term, that term by that term, this term by this term, this term by that term. Okay, and same thing here, so we're going to end up with 8 different terms here, okay, which looks a little bit nasty, so we're going to skip past that step, okay, get to our collecting like terms, which gives us minus 20 outside of sine of 4t, okay, cos of t plus cos of 4t sine of t, okay, which simplifies down to minus 20 sine of 5t. Okay, by using our addition theorems of trigonometry with sine of a plus b equals sine of a cos of b plus cos of a sine of b. Okay, so that's how we end up getting through to our nice answer here. Okay, part D. Okay, we've got to actually find the maximum and minimum values of the acceleration. Okay, so what we need to do, okay, is of course we need to differentiate our r dot of t, okay, to find our acceleration. So we've got to find the derivative of our x dot of t and y dot of t. So come over here. Okay, so we can say our x dot dot of t. Okay, well that's going to be our derivative of here. Okay, and our derivative of that is actually equal to minus 4 outside of cos of t, okay, plus 4 cos of 4t I, okay, and our y of t, okay, is equal to 4 outside of minus sine of t, okay, plus 4 sine of 4t j. Okay, so we could put them together into one big equation. Okay, but what we need to do is we've got to find the maximum and minimum values of the acceleration. So we need to find the magnitude of our acceleration. Okay, so really we're going to be finding the modulus of r double dot of t, which of course is equal to the square root of our minus 4 cos of t, okay, plus 4, so that's outside of that, cos of 4t squared, okay, and of course then it's also plus, okay, our 4 outside of our minus sine of t plus 4 sine of 4t squared. Okay, again, so that's quite big, okay, but again it simplifies down. Okay, if we were to expand those brackets out, okay, which they do go through it in the textbook, okay, with what you get, okay, and it does actually show you on the left hand side, okay, what some of the identities are that we're using. Okay, what we get to is the square root of 16 outside of 17 plus 8 cos of 5t, okay, which equals 4 outside of the square root of 17 plus 8 cos of 5t. Okay, so the maximum value occurs, okay, when this, our cos of 5t equals 1. So again, we're not actually cared about what time it actually happens at, we just want to know what the maximum value is. Okay, so our max occurs when cos of 5t equals 1. Okay, so that's going to be at 4 times the square root of 17 plus 8. 8, which 17 plus 8 is 25, so 4 times 5 is 20. Okay, our min occurs when cos of our 5t equals -1, the minimum value that we can get. Okay, so that means that we're going to get at 4 times the square root of 17. If cos is -1, okay, then we're actually going to take away 8. Okay, which means we're going to get 4 outside of the square root of 9, quite nice, which equals 12. Okay, so it's quite interesting, and it's a good little question this. You can get all the way through, looks horrible in lots of places, but we can actually find that we get quite nice values for the maximum and minimum acceleration. Okay, in part E, we need to sketch the path of the particles. So this is where it might flip over to the next page. Okay, well, we know that x equals our 4 cos of t plus cos of 4t, and our y equals 4 sine of t, take sine of 4t. Okay, now this would be horrible to sketch by hand, but we can actually put our calculator in parametric mode, okay, to sketch a graph of the parametric equations. Okay, and when we do that, okay, I'm sure my copy is not going to be very good, okay, but we find this very nice picture that looks something like that. Okay, you can see it in the textbook. Okay, so you can find when we actually do sketch our parametric equations, okay, that we do get some very interesting looking graphs. Okay, but again, you'll see in the last couple of worked examples, okay, that really is a time that we need to employ our calculator. Okay, so look, I know that the worked examples in here were quite long and quite detailed. Okay, but remember that they did have multiple parts to them, so it really just be a matter of looking at the parts that are relevant to the questions that you're doing. Okay, but just having a bit of a look at the questions here. A lot of them are longer questions like the worked examples. Okay, so I would make sure that you're looking at those when you're trying to get through the work of this section.